elements cannot be separated. Compounds can be separated by chemical changes. Bonds are broken. Bonds are intramolecular forces. So intra, within, forces are bonds. So this would represent a chemical change. We have the pink and red one. We have a compound, and we can undergo a chemical change to break that up into the red elements and the pink elements or atoms. Mixtures can be separated by physical changes because the attractions between the particles are the only thing that have to be broken. These attractions are what we refer to as intermolecular forces. Between molecule forces. So this middle picture represents our mixture. We have the red and pink particles, and then we could physically separate them into the red particles and the pink particles. So how we separate them, we can separate them by physically moving them. Sometimes, though, it's a little bit more complicated, and so we have a couple of separation techniques. The first one is distillation. When you have a solution such as Kool-Aid or Coke, or in this case, alcohol and water, it's a homogeneous mixture, and so it looks like it can't be separated out, but in reality, it can be separated. If they have a difference in boiling point, we can separate them based on boiling point. So how distillation works is we have our solution and we start heating it up. Eventually, one of the substances starts to boil. We know that it's boiling. One, we may see some bubbles start forming, and the temperature should remain constant. Remember that when a substance boils, its temperature remains constant. And so as it's boiling, the temperature is constant, and one of the gas liquids is turning into a gas and going up this tube, which then goes down this tube, and then that gas gets cooled, generally by some cold water going on the outside of the tube to help facilitate the cooling of that gas back down into liquid or condensation. Once that gas condensates, it quickly goes into this separate round bottom flask and is collected. When the temperature starts to rise again, then we know that all of this first substance has been boiled away, so we can remove this flask. We can then start collecting the next part of the solution as it boils if we had a mixture of more than just two items in there. So go ahead and pause the video and answer questions A and B on your own. Restart when you have your answer. So over here, we talked about it was a solution. Those are pretty evenly distributed, and it's alcohol and water. And so that would be a homogeneous mixture. In circle 2, if you look closely at the key, it says that I have just alcohol, which is C2H5OH in this container. And so that must be a compound because I've got carbon, hydrogen, and oxygen in the container. So is this a physical change or a chemical change? And how do you know? Go ahead and pause the video and figure out if it's physical or chemical based on what was breaking. If you said physical change, you are correct. Notice that the water and alcohol is not bonded together. They're just all mixed in there. We can also see like a water is a vapor here. So it's not bonded together. They're just mixed. And so as it's heating, it's just pulling the alcohol molecules further away into the gas form. So no bonds are actually broken, so a physical change. So is water or alcohol's attractions weaker between its particles? Go ahead and pause the video and think about who would boil off first, if it has strong attractions or weak attractions. So alcohol has the weaker attractions because it boiled first. So it took less energy to turn alcohol into a gas. Another way that we can separate a mixture is through filtration. This one's going to separate a solid and liquid mixture. So again, sometimes you can't just physically separate them with your hands, and so we can use filtration. We can also use filtration if we have a mixture of two liquids that are immiscible. Immiscible meaning one where we have different layers, they don't mix. So how the filter works, or filtration, we have a piece of filter paper, so that dotted V is the filter paper, and then that's inside of a funnel. So that's our solid lines. Our filter paper has little holes in it that we can't see with our naked eye, but those small holes allow for some particles to pass through. Like water will pass through, and anything that was dissolved in the water can pass through. But larger particles are too large and they cannot pass through the filter paper. So large particles get stuck in the filter paper, smaller particles go through the filter paper, giving us what's here at the bottom. So go ahead and pause the video and figure out what type of matter is represented in circle 1. So type of matter, we're looking for element, compound, homogeneous mixture, or heterogeneous mixture. So for A, you should have said that that was a heterogeneous mixture. Notice it's not uniformly distributed. We have a couple of the larger particles, but they're not all mixed in evenly. And then what type of matter is represented in circle 2? So down here, we're looking at the blue and black. So looking at the blue and black, how are those distributed? If you said homogeneously, then you are correct. So if they pass through the filter paper, then we won't be able to see those different pieces generally, because it's usually dissolved in the water, so evenly spread out. So is this a physical or a chemical change, and how do you know? Go ahead and pause the video and answer that one. If you said physical change, you are correct. So again, none of the bonds were actually broken. We're just pulling the molecules further apart from each other, which is breaking intermolecular forces, not intramolecular. Electrolysis is when an electric current is passed through a sample, separating it into the elements that made it up. So what you're looking at in this container is we have some copper chloride. So the copper chloride are the square circle squares, and they're in the solution. So that's what I started with. Then I put this battery with the electrodes in this solution and turned it on. When I turned it on one of my electrodes, I started getting copper metal forming on it. And on the other electrode, I started seeing bubbles and a gas being produced, which was chlorine gas. So what type of matter is chlorine? So this one here, go ahead and pause the video. And again, we're looking for element, compound, homogeneous, or heterogeneous mixture. So chlorine is an element. It's made up of one type of atom. So is this a physical or a chemical change, and how do you know? In this case, it was a chemical change. The bonds between copper and chlorine are broken, and we've made copper and we've made chlorine. So this one compound is broken up into two elements. So that's a chemical change. And so if bonds are broken, are those intermolecular forces or intramolecular forces? Well, actual bonds are intramolecular forces. If a chemical change is occurring, I'm breaking intramolecular forces. And if a physical change is occurring, such as in distillation and filtration, intermolecular forces are breaking, which are the attractions between the particles. The last one that we're talking about is chromatography. And chromatography also is used to separate a solution. And so it's used to separate mixtures by their polarity or based on their polarity. Polarity is the similarity in types of attractions the particles have between each other. So if they're very similar, then they're going to attract each other. So in chromatography, or at least paper chromatography, the stationary phase is a sheet of chromatography paper or filter paper. So here we can see the stationary phase. The mobile phase will be either a gas or a liquid. Majority of the time it'll be a liquid. The overall separation depends again on how strongly attracted the chemicals are for either the mobile phase, which is the liquid that's going to be moving up the paper, or the stationary phase, which is the piece of paper. So the substance more attracted to the mobile phase, or the liquid, is going to want to travel with the liquid and touch it as long as possible. So it's going to go the furthest up. The substance more attracted to the paper will not travel as far. So for example, here we have our chromatography setup, and they had a piece of leaf stain. And they wanted to see what chemicals made up that piece of leaf litter or leaf stain. So doing chromatography, it separated into these 4 distinct sections, which had these different pigments. So which of these pigments is the most similar to the water or the solvent that was on the bottom? Well, the one that's most attracted to the mobile phase, or the solvent, will travel the furthest up the paper. So that would be carotene. And then the one that's most attracted to the paper, or the least like the solvent or the mobile phase, is chlorophyll B. So chlorophyll B is not attracted to the mobile phase, it's more attracted to the paper. So your steps on doing a chromatography experiment is you first get a very small amount of the solution that you're trying to separate, and that's spotted onto a piece of filter paper or chromatography paper and allowed to dry. Notice that that test solution has to be a few centimeters from the bottom of the paper. Then that strip is placed vertically into a jar containing a small amount of solvent. Notice that the solvent is below the line of our test solution. As the solvent or the liquid is drawn up the strip by capillary action, it dissolves the sample. The various solutes, which are the particles dissolved in the solution, have different affinities or attraction to the paper and to the solvent, which is what the solute is dissolved in, and thus can be separated as the solvent moves up the strip. So as it's moving up the strip, it's separating them based on their attractions to either the paper or the solvent. Number 5 is an important one. It says pull the strip out of the solvent before the solvent front reaches the top of the strip. So you just want to pull it out before the liquid reaches the top of the paper so we can see how far the solvent actually went. Next, you would record the distance the solvent traveled and the distance that each component traveled. This allows us to calculate the RF value. So what that means is my solvent starts at the line of where we dotted our solution, and then it went to right here. So I can see that the liquid stopped at this point when I pulled it out. So that's my solvent front. So it traveled 5.4 centimeters. So the distance the solvent flowed, solvent being my liquid, was 5.4 centimeters. And then my component, depending on which one I was looking at, in this case I'm looking at this bottom one, I look in the middle of it, and it traveled 2.7 centimeters. Again, from where it started to the middle of that dot. So the distance the substance flowed, so 2.7 over 5.4 gives me an RF factor of 0.5. I could do the same thing for this dot, and I would just measure from the middle there. So of these two, the top dot has a larger RF factor than the bottom dot. I would only need to calculate RF values if I had a multitude of samples I was trying to separate, and I did them on separate chromatography papers. If I do them all on the same chromatography paper, like this example, then I don't need to calculate the RF factor because they all have the same mobile phase end point. So go ahead and pause the video and try these 3 questions on your own. Restart when you have an answer. So here, they want to know who has the most similar molecular structures. Well, if they're similar to each other, they're going to travel roughly the same distance on the chromatography paper. So looking over here, the two that had roughly the same distance traveled was A and D. So they must be most similar to each other. And then question 2 and 3 were similar to what we did on the previous slide. So the greatest attraction for the solvent would have traveled the most with the solvent. So the furthest up, and the furthest up was B. And if it had the greatest attraction to the paper, then it would have traveled the least amount. And so that would have been D.